because Brian's not here and we're covering lots of material and blah, blah, blah. Anyway, and I feel like I'm doing something. See, I'm doing something. I'm teaching him. Anyway, let me get the audio. And in case it doesn't work, we'll have the audio recording as well. All right, I did not grade your test yet. It's been a crazy couple of days. I won't even feel all sorry about that. But anyway, it's been a crazy couple of days. I do not have your test graded. I will. Did I ever post the grades from your second papers?
No.
Okay, they're graded. They're still on my wife's computer, and I thought I had it posted, but I guess I did not. I wanted to make sure because I was looking at my to-do list from the other day, and that was not crossed off. And I'm like, I'm sure I did it, but I didn't cross. I better ask them. So okay, I will get it, Debbie, this evening on my wife's computer, and I'll just upload those grades. It's no big deal. Anyway, I just had the wrong laptop that day, and they're on there instead. Okay, so that'll get done. Those grades will all be available to you shortly. It's just I had a million things going on. Okay, so now we're moving on to the next unit, which means we need to have another set of papers. This unit has a lot of stuff about stability and hydrostatic balance in it. It's not the only thing we're doing in this unit, but it's probably the more interesting stuff versus, I don't know, what? So, your next paper assignment will be to find something that involves stability. Okay, an actual paper that okay, there are papers out there that in great detail show you what conditionally unstable means, or shows you in great detail that your understanding of absolutely unstable, oh my goodness. Okay, that could be really cool, it could be really interesting, but that's probably not the direction you want to go, okay? I mean, as long as your paper involves something about stability, like CAPE or whatever, that's fine. I don't really want this to be, some big, like you're writing a paper that involves, or reading papers that are some big theoretical derivations or something like that. That's not so interesting. Well, actually, there's very interesting things about that. It's just not the direction I necessarily want you to go, okay? So anyway, something stability, hydrostatic balance, something like that. You aren't going to have any trouble. I mean, worst case scenario, you'll find a paper about a thunderstorm, a squall line or something, and yay, that's got stability in it, right? Yes, Dr. Sharkey, it does. I will later today take a look and figure out what day to make these things do. But we got kind of a pattern going now, right? I mean, probably by about a week from today, you'll have to have your papers. You'll probably turn in the written paper about a week and a half to 2 weeks from today. And then the talks will be the following class, you know what I'm saying? So it's probably about that same schedule. Again, I just don't have the exact dates. Again, it's on my to-do list for today. I just didn't get it done before class. So I'll send a message out once I have all those dates. But, by about a week from today, you should know what paper you're doing and have it sent to me. Okay? You guys are doing a good job with those papers. Okay. Today we're moving forward with Selby. And we're going to be talking about Chapter 6, which is hydrostatic equilibrium. Which sounds like something we shouldn't have to spend a lot of time on. I mean, hydrostatic balance is even intro students learn the term hydrostatic balance, right? What is hydrostatic balance? It's the whole business of how the vertical pressure gradient force balances the force of gravity. Good grief, it can't be all that complicated. I mean, especially once you let go of the idea that it might be magic. A lot of times students are like, I wonder why it is, right? As to why is the atmosphere in hydrostatic balance? Well, it's because it couldn't be any other way, right? I mean, at the very simplistic understanding of hydrostatic balance that we have, we're like, here's the atmosphere, here's some pressure. Let's call this 1,000 millibars, and this is some other height. Let's call it 500 millibars. There's a vertical pressure gradient force pushing from the higher pressure at the surface towards the lower pressure aloft, a very strong pressure gradient force, in fact. But that doesn't mean that air is actually moving that way. Quite to the contrary, we have the force of gravity pushing down. If we lived on a planet that had stronger gravity, all that would happen, gravity would be stronger, but these pressure layers, isobaric layers, would be closer together. The vertical pressure gradient force would be stronger. If we had a planet that had weaker gravity, these layers would be farther apart, so that the vertical pressure gradient force would be weaker. But that's all there is to it. It doesn't sound like it would be all that hard. In practice, it's a wildly complex thing as to how it actually works. And how it works on the fact that the planet is not flat. It has mountains and valleys and stuff like that. I mean, in a class like Advanced Dynamics, I don't think we call it Dynamics 3 anymore, I think we call it Advanced Dynamics. You can get all crazy complicated about how all this really works. I remember, for example, back when I was in teaching the dynamic sequence, one of the kinds of problems we did involved, what if there was a big hole? So here's the Earth with a big hole in it. Okay? Figuring out hydrostatic balance in a big, deep hole is a giant nightmare. Because, okay, air will go into this hole, right? And there'll be big, high pressure down here. But as air goes down into that hole, it's also going to be warming dry adiabatically, so it's also going to expand. It's actually really complicated to figure out, like in a deep, our ideas about hydrostatic balance kind of work on the assumption that like the Earth is kind of flat and smooth. And the actual problems I have the students do involve, see if you actually had a deep hole like this, it was actually kind of a cool problem, I should dig it up sometime. If you had this hole, see all this mass of the atmosphere that's going down into this hole? So what happens to the pressure outside the hole? It goes down, right? There's less air up there. So I asked the students that they had to figure out hydrostatic balance inside of this hole, and I want to know how deep, okay, I said what if this hole was 1 kilometer squared across? You know, that's how big it was. How deep would the hole have to be that there was like, you know, the pressure of the surface fell to, let's say, 200 millibars? You know, like you're some evil scientist, and you've dug a big, deep hole with a big stopper on it, and unless they give you $1 billion, you're going to pull the plug and all the atmosphere is going to drain into that hole? It's a wildly complicated problem to solve, and it was way too hard, but, you know, whatever. Dr. Sharkey's a jackass on tests and stuff like that, right? So, anyway, it was a fun problem, because it turns out that I think it's like 50 kilometers or something. It's not all that deep. You could have to drink the whole atmosphere would drain into it. Oh, by the way, that's because the atmosphere, there ain't very much of it, right? I mean, the atmosphere is just a thin little shell on the top of the planet. Anyway, it's a very cool problem. Hydrostatic balance is wildly complicated, again, because we are thinking about it as being on a planet that is round. Another classic weird problem is to figure out what would hydrostatic balance be if the Earth were a cube. And it turns out to be wildly complicated, and what you find out is that the Earth's atmosphere collects all right on the faces of the cube, like all the air is here, there's no air, these are effectively points out in space. And all the atmosphere collects over here. Again, Dr. Sharp is a real jackass apparently, because he would make them do things like this, but we're not going to do that. That's not the direction your textbook isn't going. It's very unusual for your textbook not to take it in a strange, crazy direction. But in this case, your textbook goes in very normal directions with this. We're not going to, so if Murray Salby could restrain himself from going a crazy direction with the problems, I will too. Okay? Thank you. I know. I'm a good guy. Rather, he just says, you know what, there's all kinds of crazy problems with this here. For example, here we go. Gravity. Gravity's way more complicated than you know. Okay, here's the Earth. Here's the center of the Earth. Here's the axis of the Earth. Here's a place out in the atmosphere or out in space or whatever. It seems like it should not be too complicated of a thing to figure out gravity. Okay, it's a vector because it's a force, and it should be pointed directly towards the axis. Towards the center of the Earth. That would be lovely. And it can be done. Hell, you all are survivors of like General Physics 1 and 2. You probably at some point actually had to even like take the universal gravitational constant in the mass of the Earth or something. You had to actually figure out the value of gravity. And you found out the value of gravity at the surface of the Earth was, the magnitude of gravity was 9.8 meters per second, and things like that. And it's a vector that points towards the axis of the center of the Earth. And that would be lovely, but it's not actually quite right. And then you would say, oh yeah, that's right. There's some crazy complication about the fact that the farther you get from the axis, from the center of the Earth, the weaker gravity gets. Gravity is stronger if you are closer to the surface of the Earth. Gravity is weaker the farther you get. And that's true now, of course, the surface of the atmosphere doesn't cover a very large area. Okay? You remember, if the Earth were the size of an apple, the atmosphere is thinner than the skin of the apple. There's really not that much difference in the force of gravity at the surface of the Earth versus, say, the top of the homosphere or something like that. Okay, but you know what? If we're going to be a pain in the ass, and hell, models are all about being a pain in the ass. I don't know what's with swearing like a sailor today. If the models, whatever. Yeah, they probably actually do someplace in the model, in the Whorf model or something like that. They probably actually have some place in the, what's the configuration, the tables, the nameless files and things like that. Is that the right word? Yeah, the nameless files. Probably you do have someplace in there where you have to set the value of gravity, but that's the value of gravity at the surface of the Earth, and then probably the model actually does compute at all the heights. Okay, but you know what? It's not a huge difference. Only a really big pain in the butt would care about the differences in that. But there's a bigger problem, and that is the rotation of the Earth. See, the rotation of the Earth creates a centrifugal force that is effectively part of gravity. As we go around the axis of the Earth, we are experiencing a centrifugal force. And that centrifugal force is pushing us away from the axis of the Earth. If I had a plumb bob, you guys know what a plumb bob is, right? It's a string with a weight on the end. and like I don't know who will use it, like a contractor would use it. When he figures out where the stud is in the wall, he puts the plumb bob there, and then he can nail here, here, and here, and he'll hit the stud, right? It's straight up and down. If you had a plumb bob, it should point straight down, according to gravity, right to the center of the Earth, right? But it doesn't. Because as the Earth is going in its, as it's rotating, there's also a centrifugal force pushing that plumb bob out. It would not point straight towards the axis of the Earth. It would only work if the Earth weren't rotating. Plumb bob is not pointing down. Down, our idea of down is a combination of gravity and the centrifugal force as the Earth rotates. Down is not just the way towards the center of the Earth. Down is a combination of the centrifugal force and the force of gravity. The true gravity, the effective gravity vector, is actually the sum of the actual physical gravity and the centrifugal force as the Earth is rotating. That means every latitude on Earth has a slightly different value of effective gravity. Even if we are going to not worry about the fact that, like, oh, here in Omaha we are higher above sea level than, say, San Francisco. There's also a difference in gravity because of that, but also because of our latitudes and so on. We all have different effective gravity vectors. Now, if you're at the equator, it's a fairly simple thing. For locations above the equator, effective gravity is basically just a weaker form of gravity. Gravity is at any given location is pushing exactly in towards the physical gravity is pushing in directly exactly towards the center of the Earth, but the centrifugal force is pushing directly out. And the centrifugal force partially cancels out. You weigh less at the equator than you do at 40 north. Because the centrifugal force, as you're going wee around the axis of the Earth once every 24 hours, is partially canceling your weight. Your weight due to the force of gravity strictly. Effective gravity is a little weaker. At the poles, there's not really all that much centrifugal force. I mean, this little circle here that we're going, gravity is still pushing down, the physical gravity is still pushing down towards the center of the Earth. There's a centrifugal force, and the effective gravity is the combination of the two, but the centrifugal force is just so small because you're going around a much, much smaller circle. But in the mid-latitudes, this can be a big difference. This is a problem, because we really want to be able to have a coordinate system where we say, x is this way, y is this way, and z is up. And altitude would be our choice. We really want altitude to be how we measure up. But the problem is, if we use, here's our z vector. It goes, we're going, I'm sorry, ij. If I use the terms ij and k, you're happy with that, right? You're all in like dynamics, right? I is in the x direction, j is in the y direction, k is in the vertical direction. Here's my k. It goes perpendicular to all these heights of, these levels of constant height. Here's one, here's k. Look, gravity has a horizontal component to it. It has a vertical component in the k direction, but it also has a horizontal component because of that centrifugal force. This is a serious problem. This is a problem for which there is not a simple way to deal with. This is a big, big problem across everything you saw in dynamics. How many times in dynamics do you have things that are, like u in the I direction plus v in the j direction plus u/v/w in the k direction, whatever, and you got all kinds of partials and crap like that. Now we have a serious problem. Because I don't really want down, I don't want my gravity to have a horizontal component. And the way we solve this problem is to get rid of our idea of height as a vertical coordinate and to switch to geopotential height. Oh, wait a minute. Now this is a term you might vaguely remember. Geopotential height. Geopotential height, okay, so these black lines that I have on here are the actual physical number of meters we are above sea level. So, these are perfect circles around the surface of the Earth. On the other hand, these red lines are contours, are levels of geopotential. And geopotential is going to solve this problem because it's not very well drawn here, because the effective gravity vector will always be perpendicular to the heights in geopotential. What you and I experience as down, when I drop something, it's not headed towards the center of the Earth, it's going perpendicular to geopotential contours. It's going from areas of high geopotential to areas of low geopotential perpendicularly across the contours. That's kind of what I mean by down anyway, right? This is actually a way better vertical coordinate than height is. Because I want gravity to be, I want to be going across these contours, that is my direction. That is when, that is the force, the effective gravity is pulling the air parcels and so on. Okay, geopotential. These geopotential surfaces are so-called oblate spheroids. What's an oblate spheroid? Did you hear that word? It's like a sphere that's bulged at the surface, right? Where have you heard the word oblate spheroid before? The Earth is an oblate spheroid. Right. That's not a coincidence, right? The surface of the Earth is on basically a geopotential surface too. All of the gas giant planets are, you can actually see how they are kind of smooshed. Okay, when you look at them like a telescope picture or something like that. They are oblate spheroids. They have this sort of smooshed shape because the top of the clouds are on a geopotential surface. The symbol that we use for geopotential is just a big V. And our effective gravity vector, G, is just negative del phi. Del being a gradient. Gradient vectors point towards high. So negative del will be pointing towards low. So it's pointing towards areas of low geopotential. So at every location, right here, gravity, if you dropped the ball right here, it would go perpendicular to these contours. If you dropped it here, it would be perpendicular to these contours. And in general, these vectors would not intersect the center of the Earth. But they are the direction that effectively gravity is pulling the objects. These are actually more important than just height. And the name geopotential is not a coincidence. I mean, they are really about the potential energy. On this surface, a same object will have the same amount of potential energy with respect to Earth's gravity and so on. Oh my goodness, that's a useful thing in lots of properties. So, alright, we will have this idea of a geopotential, and then our gravity, our effective gravity vector is, the gradient of this geopotential. And so here's what the book is actually trying to illustrate with one of those figures that I was trying to do better. At any given location then, there is a real gravity that is about physics that heads down towards the axis of the Earth, but the centrifugal force acting as this location is going around the axis of the Earth means that effectively our gravity is this way. It does not intersect the center of the Earth. On the other hand, if we could just use geopotential as a vertical coordinate, yay us, we would now have a coordinate system that does work right, where, we now, in the k direction, we are now going down. The gravity doesn't have a horizontal component or anything like that. This would work. So, geopotential has units of meters squared per second squared. Has units of meters squared per second squared. I think that actually works out to potential units of energy per unit mass, but I'd have to think about that. That's not such an easy unit to use for height. Okay? On the other hand, we can have geopotential height, Z. So this is geopotential. Geopotential height is big Z. That is in contrast to the little z that is like physically how many meters something is above ground. My pen here is 1 meter above the room, but it is not 1 geopotential meter above the floor here. It will be slightly different than that because of the rotation of the Earth. The geopotential height is strictly determined, it is this idea here on here, the geopotential height is the integral, I don't think I have this marked up on the next slide. Yes. So we are integrating, okay, so it's got 1 over g to get the unit, g naught, this is the average value of the surface of the Earth, 9.8 meters per second. 1 over g naught times the integral, integrating from the surface of the Earth up to our height z, where we are, we say we're using z, that's little z. How many meters are we going, like a tape measure? We're integrating the actual measured or computed value of gravity at that location per height. And you get that this geopotential height is just the geopotential divided by big G, or you could move big G over to the other side, whichever way. So this geopotential height has units of meters. They're units of meters, but I mean, it doesn't mean like that's how many meters it is from here to here, but it has units of meters. That was marked up right there. Does this matter? I have an air parcel that I have lifted to a height of 10 kilometers. If I had a tape measure and I dragged it down to the surface of the Earth at sea level, it's 10 meters away. Is its geopotential height 10 kilometers? No. Is it damn close to it? It actually is pretty close. I mean, it's, you know, it'll be 10,100 meters or something like that. I mean, it's within like 1% or something like that. But you know what? You've been using, when you did all this stuff in dynamics, dynamic meteorology, you often, you know, they said that was geopotential height or something like that, right? You've seen that term in synoptics, right? Yeah, what is the height of, that's 500 millibar? Oh, you know, the geopotential height's like, you know, 5,400 meters or something like that. They don't mean it's 5,400 meters above the ground, they mean it's at a geopotential height of 5,400 meters. It just so happens 5,400 meters in geopotential height, you know, it's probably 5,380 physical meters. I mean, it's close enough, right? From the point of view of just day-to-day life, the difference between geopotential height and you know, physical altitude is not all that different. In fact, with a little bit of rearranging here, we can find out that, like, for example, a change in geopotential height, you know, from the top to the bottom of a layer, is actually just the change in the physical height. You know, how many meters, dz is how many meters it is from the bottom to the top of that layer, times g over g naught. G naught is the average force of gravity at the surface of the Earth. And G is the value of gravity of that actual layer. For real places in the atmosphere, how different is the magnitude of G from the value of G naught? If our atmosphere extended out into deep space, where, you know, gravity would be much, much weaker, it would be different. But it doesn't. Gravity is, you know, I mean, gravity here at the surface of the Earth and gravity at the 500 millibar level is not all that different, right? Gravity's weaker at the 500 millibar level, so this number is always going to be less than 1. It's going to be like 0.9995 or something, okay, right? This number is going to always be very close to 1. So change in geopotential height and change in physical height, like literally how many meters it is from the top to the bottom of the layer, is practically the same thing. The change in geopotential height will always be a little bit smaller than the change, you know, a layer that is 1,000 meters thick will be a little bit less than 1,000 geopotential meters thick. But other than that, it's pretty much the same damn thing. This has implications for hydrostatic balance. If I haven't threatened people before, let me threaten people now. Make sure as graduate students you always have certain equations at the tip of your tongue. You could always, on your written exams, at your oral exam, at your defense, if it came up, the hydrostatic balance is one of the ones you got to make sure you can always remember, okay? I have to admit, it's one of the ones that I always draw a blank when I'm actually ready to write it down. I'm always like, oh crud, do I want it to be the dp on one side and the dz on the other? I don't know. It always takes me a second. And it shouldn't. It should be that much just a part of. Anyway, look, this is the correct definition of hydrostatic balance. The change in pressure with look, we can bring this dz over to this side. Look, change in pressure with respect to height was supposed to be about just the density and gravity. But here was a little secret hiding in there. That gravity was changing from place to place. Right? This gives us the opportunity to get away from that problem by saying you can replace that gravity that is changing from place to place with G naught, which we like to do anyway, as long as you just use geopotential height, which is what meteorologists are doing anyway. So when you look at a synoptic chart, I don't know if anybody ever looks at synoptic charts anymore. You know, the old paper charts, they don't even happen anymore. Whatever, you use Jetpack to make yourself a plot of the 500 millibar chart and it shows you all the heights. Those are in geopotential meters, actually usually in geopotential decameters, which, you know, whatever. Because somebody's kid was in second grade and learned all the prefixes for the metric system or something. Decimmeters? Anyway, you know, who uses that? Anyway, but yeah, as long as you're just, you know, agreeing that we're in geopotential height, then we can use the values of the value of gravity at the surface of the Earth, and all is happy. But you know what? This is a bunch of to-do about what doesn't add up to a big difference. Because throughout even the whole depth of the homosphere, the value of G is about equal to the value of G naught. I mean, the homosphere is just not that big compared to the planet. And so, there is some small difference. I have every confidence that something like WRF really does go through and compute the true value. No, it doesn't. I lied to you. It really does it all in geopotential height. Then it doesn't have to worry about the changing values of gravity. Did you see the little bait and switch I did there? That's called teaching. I made it look like it was going to be really horrible what those model people were doing. And then I said, oh yeah, what you do in dynamics, okay. They just use geopotential height instead of, the height. Then comes the sentence in Selby that just makes you want to smack him around. This is the same one, this is the same guy who had all those statements along the way that have just really upset me. Where he said things like, and therefore we can think of mixing ratio and specific humidity as the same thing. No, you can't. What are you doing? Or we can think of equivalent potential temperature and potential temperature as the same thing. I'm going to hurt you. Or the one that was worse was when he actually said, well, therefore we think of virtual temperature and temperature as the same thing. What's he talking about? This time, unfortunately, this is the truth, and is that in many ways, because the geopotential height is so similar to physical height, we generally assume that when we're talking about the same thing. And when we talk about the effective gravity, we go ahead and, the actual gravity vector may be different, but the magnitude of gravity is basically the same thing as the magnitude of gravity of the surface of the Earth over the distances in the Earth's atmosphere. It wouldn't have to be that way. We just happen to live on a planet where it works out that way. Does anybody here read the comic strip XKCD? I think you do, don't you, Sam? Or you're familiar with the What If? Because you sent me one time, didn't you?
I did.
Yeah.
My boyfriend's had one.
Oh, it's okay.
I read them sometimes.
XKCD is an awesome comic strip if you're a nerd. Therefore, I'm its core market. And this week's episode of What If, he's a scientist who makes very cool comics explaining things. And this one's was, what if the whole Earth was crushed down so it had same amount of mass, but it was only, I think it was like 2 meters across or something like that. It was The Little Prince. You guys ever read The Little Prince when you were a kid? Anyway, the guy lived on a planet that was like 2 meters across. He lived on an asteroid that was 2 meters across, and he was the Little Prince in there, and you could walk around the whole planet like, 2 minutes or whatever. Anyway, and he talks about all the cool things about the atmosphere and stuff like that, and the forces of gravity if the whole Earth were only like 2 meters across. Like, for example, the force of gravity at the prince's head was half of the force of gravity at his feet. And it's very cool, and like, it talks about the changes in the atmosphere at, when the planet is that. Anyway, it's very cool. We don't live on a planet that has that kind of mass in a volume of, 1/10 billionth of our planet. Therefore, we get to make these kinds of assumptions. Okay? I will make it Samantha's problem to run the WRF for a planet 2 meters across that has no. Okay? I suspect it breaks all kinds of other violations. But anyway, it was awesome. I was like, wow, changes in gravity with respect to height on a comic strip just Tuesday when it came out. I was so happy. Okay, so let's talk more about hydrostatic balance. A nifty other way we could write hydrostatic balance would be to rearrange it this way, right? We pulled there was a rho on this side, we pulled it over to that side, and we made it into an alpha, right? Like 1 over rho. Okay, so one of our ways that we could rewrite hydrostatic balance, and look at us already cheating. Okay, no, we aren't necessarily cheating. Okay, we are either playing ridiculously fast and loose, and we really mean gravity at the surface of the Earth, and we really mean geopotential height, or they're telling us the truth here. They really mean as in measure the force of gravity here, is that combination of physical gravity and the rotation of the Earth, and literally measure the physical number of meters between there. That sounds like the hard way to do it, but whatever. They're right. They have this written in their textbook. It's just they're doing it the hard way. Okay. Well, one thing we could do with this is we could apply some. We could do some algebra here, and eventually apply the ideal gas law. We could take that form of the equation here. We could pull this G over to this side. And then we can apply the ideal gas law to that alpha. It's equal to, RT over P. I got that right there. Okay. Now, why would we do that? Because everybody's favorite evil thing to do in calculus is to get something that's got like dx over x, or in this case dp over p. Any kind of process that you know is really changing logarithmically, like pressure is changing, decreasing logarithmically with respect to height, that's what you should be looking for. Because dx over x is going to involve forms that involve log of x, right? We know that the height is going to change, the pressure is going to change with height in a logarithmic kind of way. So look, they rearrange. Oh, look, we got this over here. Now we got dp over p. All right. Well, dp over p, one way to rearrange that is that's d log p. That's one of the ones I can never remember. I mean, like we're not integrating this right now. I always forget that dp over p is also d log p, but whatever. Okay. All right. So now, way back in the first unit of the course, we learned about scale height. Where scale height was this, it was this measure of how fast pressure was changing with respect to height. If you remember what scale height was, it was how many meters it was between the top and the bottom of a layer, where the bottom of the layer had some pressure, and the pressure at the top of the layer was that pressure divided by E. It was the E folding distance in the atmosphere, is the right word for that? Okay, so the scale height. Well, look, the scale height is just R times, look at them being sloppy all over the place. Where's our RDs and stuff like that? Man. Whatever. They make such a big deal, and then we move on. Okay. RD, T over G is scale height. And look, RD, D over G. Hey, all right, we can play some games here. We can swap in that scale height, and we can get that the change in height is related to changes in pressure by the scale height. Pressure changes logarithmically with respect to height and the scale height. The scale height had hidden in their temperature. Now, when we talk about scale height in the context of like the first chapter, pressure of the surface was 1,000 millibars. The top of their layer here will have a pressure of 1,000 divided by E, or about 200 millibars, something like that. What's the average temperature of the layer between 1,000 and 200 millibars? Oh my goodness, what could be pretty much any damn thing we picked, right? Okay, now, I mean, let's face it, that's a big span of the atmosphere, from like near the surface to near the tropopause. And it's going to be dependent on the average temperature in between there. Okay, now, let's forget about that, this idea of this equation here works just fine no matter what the top and the bottom of our layer is. We're just describing how the rate of pressure is changing inside that layer. I mean, it's decreasing at the scale height, and it's decreasing logarithmically. So we could have other layers. We could have a layer here, we could have a layer here, whatever here. And notice what the scale height depends on. The temperature. That's a constant, and well, we're going to pretend that's a constant nowadays. All right? It depends on the temperature. In fact, the scale height only really depends on the temperature of the layer. Okay? So, this little idea here basically is telling us about, oh, I love how that occasionally happens. Okay. Anyway, about how thickness of layers is related to temperature. The distance between the top and the bottom of a layer is going to be related to the scale height. Okay? If this is some pressure and this is some pressure here, we have a change in log P. The change in meters between here and here just depends on H, the scale height, which itself only depends on the temperature of that layer. But you knew this already, because you knew that if you have a layer of the atmosphere and it has some, let's say 1,000 millibars at the bottom and 500 millibars at the top, how many meters it is between the top and the bottom only depends on one thing: the average temperature in that layer. Anybody remember what that's called? It's the blank equation. It starts with an H. Hypsometric equation. The hypsometric equation is this idea about thickness. I hate that word thickness. Have I told you about my aversion to the word thickness? I'll tell you about it in just a second. The thickness of a layer depends only on the temperature of the layer. In a more strict sense, it only depends on the virtual temperature of the air. Is that where you're going with being unhappy with this? I can see there's unhappiness on Samantha's face.
Density?
Well, but density is temperature of the, yeah, right. Because you already know, yeah. It's actually only, it's strictly speaking only the virtual temperature of the air. In fact, I'm guessing that if we went through and actually worked through the derivation, My guess is Salvi pulled a sneaky one on us, and this is his little, but temperature is the same thing as virtual temperature assumption. Look at that, Samantha, another teaching moment. I pulled back something from like 20 minutes ago. I've just been complaining about Salvi swapping in TV. Can you tell that sometimes lectures are more prepared than others? I actually was prepared for that. Okay. Remember that teacher evaluation time. Sometimes he's prepared. Okay, sometimes. So, the thickness of a layer only depends on, technically speaking, the average virtual temperature. I'm willing to take Salvi's little, or certainly speaking, the temperature of that layer. So a place where the layers of the atmosphere are cold, they are less thick, and a place where the layers are warmer, they are more thick. This is where I hate that word thickness. To me, the word thickness implies, like as in density, like how thick and goopy it is. But that is not the sense of the word thickness they mean. I hope I'm not confusing anybody. They actually mean it in the sense of like thick as a book, like how far it is from the top to the bottom. Okay? I've always wished that they had chosen a better word there. Okay? Cold layers are less thick, the warm layers are more thick. And it only depends on the temperature. The mean temperature of that layer. This is why we use things like thickness of a layer in, say, snowfall forecasting, like the rain-snow line. Did you guys ever learn that, like in synoptic or something like that? You had, at some point in a synoptic meteorology class, you had to learn that like some thickness line on a 1,000 to 500 millibar thickness chart was going to be the rain-snow line. Okay, I don't know, what did you learn? 5,400 or something like that was your, with a 540 decameter line, just to throw up decameters. Oh look, and those are actually geopotential meters teaching. Ta-da! I stuck the landing on that one. That is the 5,000, empirically we have found that the 5,400 meter thickness line for 1,000 to 500 millibars is how thick that layer, how warm that layer can be that a snowflake will make it through it. Any thicker than that, the average temperature of that layer is too much, snowflakes won't make it through it, they'll melt. Less thick than that, if the layer is cold enough, it won't have melted. Real operational meteorologists know tons of those kind of magic numbers. They're, they would say that's a pretty darn thick layer. They'll know like the 1,000 to 850 millibar thickness to get the rain-snow line, or they'll know that the 700 to 850 millibar thickness needs to be this, and it'll be freezing rain instead, or some such thing. Okay, I mean they know that's what they do because they learn all those kinds of numbers. Thickness as being a way of talking about the mean temperature of the layer. Neat. Which discovered about that? I mean, he's trying to do this. He's taking way too much effort here. So it's showing here that, like, here's the change in thickness, a change in height, the difference between the top and the bottom. Well, that isn't strictly what that is. Change in height is actually an infinitesimal. It's the actual differential itself. Strictly speaking, we need to integrate it from the bottom to the top of that layer. Well, the integral of dz is just z. So then z at 1 and z at 2, and that's just what an integral is. But the difference between the height at the top and the bottom of the layer, that is thickness, which there's no good meteorological symbol for. Your book is using delta z. I noticed another textbook uses th as the thickness. That seems kind of lame. There's no good meteorological symbol for thickness. If you've ever heard one, please let me know. And when you actually compute this here, you get that it is the average value of the scale height times the log of the difference between the pressure at the top and the bottom of the layer, where this little angle bracket here is his nifty way of saying average over that layer. Strictly speaking, you need to compute the average temperature in that layer in order to do this. I believe that strictly speaking has to be the mass-weighted average to make this work right. But whatever, so the temperature at the bottom counts a little bit more than the temperature at the top. Whatever. He's working way too hard to say the same thing. Plug this bad boy in here, you'd see that the only thing that determines the thickness of that layer is the average temperature of that layer. And then remember his stupid thing about it's actually virtual temperature. Strictly speaking, that is the one that we call the hypsometric equation. What does the word hypsometric mean? Nobody's making eye contact. Brian. Reflex. Sorry. Hypso is a prefix that means height. Probably in like high school geometry class, you had to use a hypsometer. A hypsometer is a big bunch of nothing. It's just a straw, I believe. You basically stood like a distance away from your school building, and you sighted in with a straw to see the top of the building, and then you measure the angle, like somebody came over with a protractor and they measured the angle of the straw and how far away you were from the building, and from that you could figure out how high the school was. It's trigonometry, right? You know, whatever. It was a big deal when you were like 10th grade because you got out of school for a little while, go outside and you can do that. All right, hypso means height. Isohypsis, the line's a constant height, stuff like that. Metric, measuring, height measuring equation. What the hell? Height measuring equation? Why would we call it that when this is about thickness? Because this, oh, I can't go into that, is really how radiosondes work. Okay. Let's clear the air about how radiosondes work. Since we've got folks in this class who have really done operational meteorology, which makes me the doofus. Who's here, like as your position or whatever, things that you've done, or internships or whatever that you've done, has done launching of balloons? Yeah? Yeah? Okay. Yeah?
Yeah.
Alright. Yeah. Alright. Now you launch the balloons. Balloon flies away. Got all kinds of equipment on board. I can bring a radiosonde in if you guys want, but you guys, several of you have already seen one. I got one too.
There's like one in the office.
There's one in the office now?
For our grad office.
Oh, really?
There's a used one somewhere.
Yeah,
We showed it for the, when the undergrads did the atmospheric science club.
oh yeah? Well, that's cool.
Board, yeah.
I actually have one, I wonder what I look like in the video right now. I'm picturing that I only see it from about here up. Whatever. Only Brian, so we're going to watch it. I was talking about radiosondes one time in intro, and the student raised his hand and goes, "Hey, one of those landed on my porch the other day." And I was like, "Yeah, right, but whatever." And he brought it in, and son of a gun, he was right. he brought in he had a radiosonde from his porch. Anyway, and I said, "Can I keep it?" And I kept it. Anyway, so I have one too. Okay, they fly away, and they take the measurement. Okay. And you know what you get from those things. It radios back, hence the term radiosonde. Its temperatures, and its pressures, and its humidities, and that's about it. And how does it know what height it's at? Give me the wrong answer first. How does it know what height it's at? GPS. Okay. Do you know that's wrong? There are such things as GPS sondes. In fact, most radiosondes these days do have GPS on board them, but they are not measuring their height with them. GPS is terrible technology for measuring height. It has to do with the geometry of where the satellites, as they pass over the location. The satellites are better. GPS technology produces estimates of your horizontal position much more accurately than your vertical position. Okay? If I just park my GPS on my cell phone outside this building here, it's going to go, and I turn it on so that I can see the height it goes. From like 1 second to another, it'll have surprisingly large errors in its estimate of how high it is. You let it run for an hour, it'll average out just fine, and then you'll have a very accurate, but a radiosonde can hang around for like an hour, okay? Radiosondes can't measure their height using GPS, okay? They can measure their horizontal position, which can be how they measure the wind, okay? They know they're right here right now, 2 seconds later they know they're at this location. They actually do it in steps larger than like 2 seconds, and then they assume the balloon is just moving with the wind in that layer. That tends to be what the GPS on board is for. If they have that kind of GPS technology on board, do anybody know what they're called? They're strictly speaking no longer called a radiosonde. GPS sonde. That is a term that will never catch on. Okay. But your garden variety weather balloon that you launch out, then, you know, we've had a couple launches now out here on the front lawn. I think we haven't had one yet this semester, have we? But last year we had some out there on the front lawn, because Dr. Zender has this thing for launching balloons. He has equipment. It's not like he has a thing for launching balloons. No, that's not it at all. He has the equipment to launch balloons. Yeah, thank you for launching balloons. That sounds bad. Anyway, no, and so your garden variety weather balloon radiosonde does not have a that isn't how it determines the height. It does it using the hypsometric equation. In my undergraduate level, 500 level version of this class, we actually then do a painstaking lab where they actually take data from a real radiosonde and they actually compute the heights doing this all the hard way. I think I have better things to do with your time, like derivations, than the grunt work of cranking through all those equations over and over again. So let me tell you how it works, though. When the balloon's parked here at the ground, it knows the temperature. Then it flies for like a second. It takes the temperature again. Okay? When it was parked here on the ground, it knew the pressure. 1 second later, I think it does it actually technically in 2 seconds. 2 second intervals later, it knows the, let's stick with one just so that it makes it church. 2 seconds later, a second later, it knows the pressure, because it does have a little aneroid barometer on board. Okay? So now let's say it's working at, let's just say the 1,000 to 999 millibar level, layer. There's a layer here. It knows the temperature at this layer. Actually, technically, it knows the temperature and the moisture at this level. It knows the temperature and the moisture at this level, at the top. So it now knows the virtual temperature at the bottom and the virtual temperature at the top of the layer, which means it now knows the average virtual temperature in this layer, which means it knows the thickness of this layer. This was height 0. This is some, 0 meters. This is how thick it is. So now what's this height? 0 plus that thickness. Okay? It now knows the height it was 2 seconds, a second after launch. Another second. Nope. Okay, it knew the temperature and the moisture here, so it knows the virtual temperature here. It knows the temperature and the moisture here at second 2, so it knows the virtual temperature here. Now it knows the average virtual temperature of this layer. Therefore, it knows the thickness of this layer. The bottom of this layer was at some known height now. So now the top of this layer is some known height. Yippee! Lather, rinse, and repeat. Right? It's a loop. Just keeps going. Every 2 seconds or second or whatever, it just computes the thickness again, and it just stacks those layers up. When I first tell undergraduate students about this, they're like, that can't be right. Yes, it is. Okay? They really do compute the height. They actually measure the height of this thing using the hypsometric equation. And if it might seem like, boy, this would be a very error-prone thing, gee, well, wait a minute. I mean, let's say I'm a little off on these temperatures here. I mean, if I'm off on the temperature here, the next layer is just sitting on top. I mean, I can't get better after that, right? I mean, if I was off on that temperature, now I have a bias as I'm going up. And what if I'm off on all the temperature? Well, if you're off on all the temperatures, yeah, you're screwed. Okay, but your radius, that's why radiosondes cost $500 each. Okay, they're a highly calibrated piece of equipment. You guys know radiosondes are expensive, right? I don't know if they're all I think nowadays there's some cheaper ones you can buy less than that. But like an official National Weather Service radiosonde is like $500. That's why they want them back. You guys know that they want them back, right? There's all that labeling on the box. When the radiosonde crashes, it says, harmless weather instrument.
I just ignored it.
You just ignored it because you kept it. Oh yeah, totally, so did I. Whatever. They want it back. They want to refurbish it and get it back. Do you want a fraction of them to get back? For the radio show one time we tried to find out. Good estimates are about 1 to 2% of them ever come back. Because most of them land out in a field someplace and a farmer runs them over, and whatever. It's just no big deal. Anyway, but they try at least to refurbish some of them. Yeah, so as long as the thing is in good working order and it doesn't have a bias, I mean, if one level, something went wrong and it measured the humidity wrong or measured, so what, okay, you'll be a little bit off, but you know what, how far off can you be on a layer that's 1 second thick as the balloon passed through it? You're not gonna, it's not going to tell you that that 1 second layer was a kilometer thick. It's going to be the difference between it saying that layer was 2 meters and that layer was 2 meters and 1 centimeter. Right? How far off are you going to really be? So the students then dutifully sit there and they have a big worksheet they work through. Okay, for this layer they get this temperature and this moisture, so they get this humidity. they get this virtual temperature. Let's compute the average virtual temperature. It's a big calculator exercise. And they work and they work and they work and they work and work. And they get the final virtual, the height at like 500 millibar. They work all the way to 500 millibar. I'm so mean. Oh crap, you guys are probably going to take that class later. If you guys end up taking the undergraduate version, I'm not mean. This is the learning experience. Anyway, if you guys don't take that class, then it was me. And you find out that they get an answer within like a meter of what the National Weather Service's official answer of what the height of the was. That is really how the balloon did it. Which is crazy. And it's amazing. And it works that well. If they do it all right, and most of them have made like rounding errors or calculator errors and they get far off.
Good Excel.
It would be an awesome Excel experiment. That's how I made the key. Because like Dr. Shaggy's going to really sit there and talk about a calculator. And he doesn't even know what a calculator. Anyway, yeah, so it's a good experiment. That is really how they do it. How radiosondes actually compute the height as they go. There was one more thing I was going to tell you about that before we moved on. They're trying anyway. In case you didn't know, radiosondes are, in many ways, awful pieces of technology. Their humidity sensors are garbage, and their temperature sensors are slow. If you move through, if Here, you got your radios on, and like you bring it, you're outside, you turn the thing on, but you're holding it. Walk from outside to inside on a hot summer day so the temperature changes. Yeah, don't do it to yourself. You'll be so disappointed as to how long it takes the radios on to figure out the temperature has changed. And you're like, wait a minute, we get our weather information from this thing as it floods away. If it goes through an inversion, I'd really like to know. I know, we all. The humidity sensors are garbage, garbage, garbage. They'll frequently report humidity is less than 0. They will, they're garbage. They do the best they can, okay? We use the information we have. The winds you get from radiosondes are really, really tricky. I made it sound like it's an easy thing, like you just take the GPS coordinates from the radiosonde here, and a few seconds later from here, and you take the difference between their coordinates and so on. Well, first off, there's inherent error in the GPS system, right? I mean, from second to second, there's error in there. Plus, the radiosonde is hanging from several meters of string below the balloon, usually quite a few. Ever watch a radiosonde launch? Whee! Whee! The radiosonde is swinging every which way. So, like, if you actually take the raw data from a radiosonde launch and, like, plot it, it looks like the winds are like, wiggle, 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 as it goes up. Because you're really just seeing the radiosonde swinging back and forth on that string. It's bad technology, but it's also the only thing we have, really. I mean, so we can't do anything about it.
So that's kind of scary, because,
It's all kinds of scary.
well, up at Fort Wainwright, where I was, we used those extensively, the sounding to forecast and tell pilots, hey, what are the winds, where's the inversion?
Yeah. Well, there's all kinds of crazy quality control that goes on. Okay, the actual raw data that comes off of a radiosonde is surprisingly garbagey, but that's a whole thing, right? People get their master's degree and go off to work at the World Weather Building in Washington